Welcome. Today we are going to discuss size of the test and power function of the test for log normal distribution and also one discrete distribution. Okay, here the question is given a random sample of size n from log normal with mean mu and variance sigma naught square distribution. For testing H naught, mu is less than or equal to mu naught versus H1, mu is greater than mu naught. And the test function is given by phi of summation log xi equal to 1 if summation log xi is greater than k, 0 otherwise. Determine k such that size of the test equal to alpha and obtain the power function of the test. So this is the question, right? Here we want to determine the value of k such that the size of the test is alpha and also obtain the power function of the test, right? Here given that the random sample of size in from log normal with mean mu and variance sigma naught square, right? What is the PDF for log normal distribution? What is the PDF? If x follows a log normal with mean mu and variance sigma square, then PDF of log normal is 1 by square root of 2 pi 1 by sigma into x e power minus 1 by 2 log x minus mu whole square divided by sigma square, right? If x follows log normal with mean mu and variance sigma square, then the PDF of log normal is 1 by square root of 2 pi 1 by sigma into x e power minus 1 by 2 log x minus mu whole square divided by sigma square, right? What is the difference between PDF of normal distribution and log normal distribution? Here one term extra, right? X 1 by x, and also here instead of x in log normal we can use log x, right? There are some properties in log normal. That is, if x follows normal with the mean mu and variance sigma square, then exponential of x follows log normal with mean mu and variance sigma square. Understood? If x follows normal with mean mu variance sigma square, then exponential of this x follows a log normal with mean mu and variance sigma square. And another one property is that if x follows log normal with mean mu and variance sigma square, then log of x follows normal with mean mu and variance sigma square. If x follows log normal with mean mu and variance sigma square, then log x follows normal with mean mu and variance sigma square. Understood? Then here is given that summation log xi, right? The test function is given that phi of summation log xi, right? If x follows log normal with mean mu and variance sigma square, then summation log xi follows which distribution? Here we know that if x follows log normal with mean mu and variance sigma naught square is given, that right, mu and sigma naught square, that means sigma square is none, right? Then if x follows log normal with mean mu and variance sigma naught square, then what? Summation log xi I from 1 to n, which follows normal with mean n mu, variance n sigma naught square. Understood? If x follows log normal with mean mu and variance sigma naught square, then summation log xi follows normal with mean n mu, variance and sigma naught square. Understood? And here we have to determine the value of k, right? First we have to know what is the size of the test, right? What is the size formula? Size equal to supremum of expectation of, in this case, expectation of phi of summation log xi I from 1 to n, right? Under h naught, right? Here under h naught, right? What is h naught here? H naught is mu less than equal to mu naught, right? Then here supremum expectation of phi of summation log xi under h naught, that means mu is less than or equal to mu naught, right? So here we have to find out for the which value of mu expectation of phi of summation log xi attains supremum value, right? For that we have to continue the same procedures we written in last problems, right? So we want to define what is beta of mu, right? Beta of mu equal to expectation of phi of summation I 1 to n log xi, right? Log xi. Then we want to know whether beta of mu is increasing function or decreasing function, right? So we can solve that. It's equal to, what is that expectation of phi of summation log xi is equal to 1 into probability of summation log xi is greater than k plus 0, right? So here 1 into probability of summation log I1 1 to n log xi is greater than k plus 0, right? Then it's equal to probability of summation I 1 to n log xi, right? It's equal to greater than k, right? It's equal to, we can take these summation log xi as a y, okay? Let y equal to summation I 1 to n log xi, okay? Then this is probability of y is greater than k, right? Then y follows which distribution here? Let y equal to summation log xi, then y follows normal n mu and sigma naught square, right? Right here, see this summation log xi follows normal n mu and sigma naught square, right? Then here it's equal to, we can write this term as integral over, here lower limit is k, right? K to infinite f of y dy, right? It's equal to integral over k to infinite, what is f of xy? So f of y is a PDF of n mu and sigma naught square, right? That is 1 by square root of 2 pi 1 by square root of n sigma naught square e power minus 1 by 2 y minus n mu divided by square root of n sigma naught square, right here, square, right, then dy. This is the PDF of y, normal, n mu and sigma naught square, right? 1 by square root of 2 pi, 1 by square root of n sigma naught square, e power minus 1 by 2, then y minus n mu whole square divided by square root of n sigma naught square into dy, right? Which is equals, that is beta of mu equal to, so you can write this probability of y is greater than k as here y follows normal with mean and mu, variance and sigma naught square, right? So we can transform these normal variable into standard normal variable, that is probability of y minus its mean, what's its mean is n mu, right? Then divided by standard deviation, that is n sigma naught square, right? Greater than k minus its mean, that is n mu divided by its standard deviation, right? It's equal to probability of z, that is standard normal variable, which is greater than k minus n mu divided by square root of n sigma naught square, that is beta of mu, right? It's equal to integral over lower limit is k minus n mu divided by square root of n sigma naught square, right? N sigma naught square, upper limit is infinite, right? Then f of z dz, right? What is f of z here? Integral over n mu square root of n sigma naught square to infinite. What's f of z here? Z follows standard normal, right? Then what is PDF of normal, standard normal distribution? Is 1 by square root of 2 pi e power minus z square divided by 2, right? 2 into this dz. That is beta of mu, right? So we have to differentiate beta of mu, right? So here the limits contains the parameters, right? The mu and sigma naught square. But the PDF f of z is not contains any, it's not depending any parameters, right? So we can use a Leibniz rule for differentiation. That is, we can take this term to this term for differentiation. Okay, that is using Leibniz rule, beta dash of mu equal to here 0 f of infinite into differentiation of infinite, right? That is 0 minus then f of lower limit, that is f of lower limit. What is lower limit here? F of k minus n mu divided by square root of n sigma naught square into its lower limit differentiation, that is d by d mu of k minus n mu divided by square root of n sigma naught square, right? Which is equal to 0 minus f of k minus n mu divided by square root of n sigma naught square equal to, so here we have to substitute z as this value, right? It is 1 by square root of 2 pi e power minus, in the case of z can use this value, k minus n mu divided by square root of n sigma naught square whole square divided by 2, right, into this differentiation, that is minus n divided by square root of n sigma naught square, right? So here minus minus, right? Minus could cancel. Then you can write this term as n by square root of 2 pi 1 by square root of n sigma naught square e power minus k minus n mu divided by square root of n sigma naught square a whole square divided by 2, right? Whether this value is greater than 0 or less than 0. So this is greater than 0, right? Which implies beta dash of mu is greater than 0, right? Therefore, beta of mu is non-increasing function or decreasing function. Beta dash of mu is greater than 0, then beta of mu is non-decreasing function, right? Non-decreasing function of mu, right? Then under h naught beta of mu attains supremum. Beta of mu attains supremum at mu equal to, for which value? What is h naught here? H naught is given that h naught is mu is less than equal to mu naught, right? And here we obtain that beta of mu is a non-decreasing function, which means it's a increasing function, alright? So here upper limit is mu naught, right? Here 0 or infinite 0. This is mu value, right? This is beta of mu value, so it's a increasing function. Then beta of mu attains supremum maximum at mu equal to mu naught, right? That is at under h naught beta of mu attains supremum at mu equal to mu naught, right? Then what is the size of the test? Then the size of the test equal to expectation of summation I 1 to n log xi under mu equal to mu naught, right? And then expectation of summation log xi under mu naught is same as supremum value of expectation of summation log xi under h naught, right? So it is equal to probability of summation log xi, which is greater than k, right, under mu naught, right? And here it's given that size of the test is given that size of the test is equal to alpha, right? So which implies, so here the size of the test is probability of summation log xi is greater than k under mu naught, right? And in the question is given that size of the test equal to alpha. Then we can write these as alpha equal to probability of summation log xi greater than k under mu naught, right? Which implies we can write these down as standard normal variable, that is probability of z, which is greater than k minus n mu divided by here n mu naught, okay, n mu naught divided by square root of n sigma naught square, right, which is equal to alpha. So here we have to determine the value of k, right? So we can take this term outside, that is k minus n mu naught divided by square root of n sigma naught square, which is equal to, here z value is, here probability of z is greater than this term equal to alpha, right? Then we can write it as k minus n mu naught divided by square root of n sigma naught square is equal to the z alpha value. So z alpha value is determined from the standard normal table, okay? So which implies, what's the k value then? K equal to z alpha square root of n sigma naught square, z alpha square root of n sigma naught square plus this value, right? And mu naught. Understood? Then k equal to n mu naught plus z alpha square root of n sigma naught square. This is the value of k, right? Then here, what is the rejection region? What is the rejection region here? So from the test function, we reject h naught. We reject h naught when probability of when log xi is greater than k with probability 1, right? We reject h naught with probability 1 when summation log xi is greater than k, right? So that is this is the rejection region, right? From the test function, that is the rejection region. So here rejection region is equal to summation log xi I 1 to n, which is greater than k, right? Which implies summation log xi I1 to n, which is greater than, what is the k value here? K value is n mu naught plus z alpha square root of n sigma naught square, right? Which implies, so here we can use standard normal table, right? So this value, for using that table, we can find what is the critical region using that table. Okay, that means we have to find out whether for the which value of z alpha, based on the which value of z alpha, what is the rejection region for this test. Okay, for that we can make some transformation here. That is summation I 1 to n log xi minus n mu naught divided by this square root of n sigma naught square, which is greater than z alpha. Summation log xi minus n mu naught divided by square root of n sigma naught square greater than z alpha. Then we reject the h naught. Okay, this is the rejection region. Then what is the power function of the test? Then power function of the test, that is beta of mu, right? What does the power function mean? Power function is rejecting h naught for the various values of parameter on the parametric space, right? It is expectation of phi of summation I 1 to n log xi under parametric space, right? Is equal to probability of summation log xi is greater than k and the parametric space. So which implies it's equal to probability of, we can make this as standard normal, right? For that, summation log xi minus its mean, that is n mu, right? Here under parametric space. So for that, here mu naught, you say mu, right? Divided by square root of n sigma naught square, and which is greater than k minus n mu divided by square root of n sigma naught square, which equal to probability of summation log xi minus n mu divided by square root of n sigma naught square is greater than, what is the value of k? Here k is n mu naught plus z alpha square root of n sigma naught square, right? Minus n mu divided by square root of n sigma naught square, right? Which equal to probability of z, which is greater than n mu naught plus z alpha square root of n sigma naught square minus n mu divided by square root of n sigma naught square. This is the power function for this test. Understood? This problem is similar like the last problems, right? So next we will go for a discrete distribution problem. Okay, and the question is, let x be a discrete random variable with the probability of x equal to 1 equal to 1 minus probability of x equal to minus 1, which is equal to p. It's equal to p. Then given a random sample of size 2 from this distribution for testing h naught p equal to p naught versus h1 p is equal to p1, where p naught equal to 0.2 and p1 equal to 0.8, and the test function is given by phi of x equal to 1 if x1 plus x2 equal to 2, 0.25 if x1 plus x2 equal to 0, and 0 if x1 plus x equal to minus. Then the question is compute the size, power, and power function of the test. So this is the question. And the question is, let x be a discrete random variable with the probability of x equal to 1 minus probability of x equal to minus 1 equal to p. Given a random sample of size 2 from this distribution for testing h naught p equal to p naught versus h1 p equal to p1, where p naught equals 0.2 and p1 equal to 0.8. okay, and here the test function is 1 if x1 plus x2 equal to 2, 0.25 if x1 plus x2 equal to 0 if x1 plus x2 equal to minus 1. And here we have to compute the size of the test, power function of the test. Okay, so here it's given that x is a discrete random variable and probability of x equal to 1 equal to p, right? Sorry, probability of x equal to 1. So in this problem it's given that probability of x equal to 1 equal to p, right? Equal to p. Then what is probability of x equal to minus 1 here? Then here we know that probability of x equal to 1 equal to p, right? This equal to p, right? Then what is probability of x equal to minus 1? What is x equal to minus 1 then? It's also p, right? Equal to 1 minus p, right? Equal to 1 minus p, right? That is 1 minus p equal to p, right? Here in this value, if you substitute these as 1 minus p, then 1 minus p equal to p, right? This value. Okay, here probability of x equal to 1 equal to p, probability of x equal to minus 1 equal to 1 minus p. From this we can write it as probability of x equal to 1 equal to p and probability of x equal to minus 1 equal to 1 minus p, right? So here in this problem it's given that n equal to 2, right? Then what is the size of the test formula here? Size equal to supremum value of expectation of phi of x, expectation of phi of x, then under p belongs to p naught, right? Size of the test equal to supremum of expectation of phi of x under p belongs to p naught, right? That is psi is equal to expectation of phi of x here under h naught is given that p equal to p naught, right? So we can take here p naught. Expectation of phi of x under p naught is equal to supremum value of expectation of phi of x under h naught, right? So it's equal to, what's the value of expectation of phi of x under p naught here? The test function is given that, right? 1 if x1 plus x2 equal to 2, 0.25 if x1 plus x2 equal to 0, 0 if x1 plus x2 equal to minus 1, right? So what's the expectation of phi of x? 1 into probability of x1 plus x2 equal to 2 plus 0.25 into probability of x1 plus x2 equal to 0 plus 0, 0, right? This time is 0, right? So we can write expectation of phi of x under p naught as 1 into probability of x1 plus x2 equal to 2 under p naught plus 0.25 into probability of x1 plus x2 equal to 0 plus 0, right? From the test function we can write expectation of phi of xi equal to 1 plus probability of x1 plus x2 equal to 2 plus 0.25 probability of x1 plus x2 equal to 0 under h naught, right? So we can write these terms as 1 into, when x1 plus x2 equal to 2, so we can write these terms as probability of either x1 equal to 1 and x2 equal to 1, then x1 plus x2 equal to 2, right? So we can write these terms as x1 equal to 1, x2 equal to 1 and the h naught plus 0.25 into here x1 plus x2 equal to 0, right? So there is two cases, right? The first case is x1 equal to 1 and x2 equal to minus 1, right? If x1 equal to 1, then x2 equal to minus 1, then x1 plus x2 equal to 0, right? Or another case, what is the other case? It is probability of x1 equal to minus 1 and x2 equal to 1, right? Plus 0, right? So x1 equal to minus 1, then x2 equal to 1, then x1 plus x2 equal to 0, right? Is it clear this time? Then it's equal to, so we can write these term as probability of x1 equal to 1 into probability of x2 equal to 1. Probability of x1 comma x2 equal to 1, we can write that term as probability of x1 equal to 1 into probability of x2 equal to 1 under p naught, right? Place, and here these term 0.25 into, we can write this term as probability of x1 equal to 1 and p naught into probability of x2 equal to minus 1 under p naught. So the first term, okay? Or we can write or as plus, right? Plus the second term. What is that? Probability of x1 equal to minus 1 under p naught into probability of x2 equal to 1 under p naught, right? Is it clear? You can write these terms as these probability of x1 equal to 1, x2 equal to minus 1 as probability of x1 equal to 1 into probability of x2 equal to minus 1 under h naught under p naught, right? So here, alright, we can write it as plus. You studied right in probability theory. Then it's equal to, we know that what is probability of value? Probability of x1 equal to 1 is p, right? And probability of x equal to minus 1 is 1 minus p, right? So here probability of x1 equal to 1 under p naught is, we know that probability of x equal to 1 is p, right? Small p, this small p, right? Then here under p naught, right? Then we can write it as p naught, right? Into, and also here probability of x equal to 1 is p, right? Small p. Then here under p naught, right? Then instead of p we can write p naught, right? Plus 0.25. Then here probability of x1 equal to 1, right? So we know that probability of x equal to 1 is p naught, p, right? Under, but here under p naught, right? So that is p naught into probability of x2 equal to minus 1, right? And we know that what is the minus 1 value? Probability of x equal to minus 1 is, minus 1 is 1 minus p, right? And here under p naught, right? It is 1 minus p naught, right? Plus here also probability of x1 equal to minus 1, right? That is 1 minus p naught under p naught, right? Then here probability of x2 equal to 1, that is p. Here p naught. Understood? It's equal to p naught square plus 0.25 and here we multiply this term, then we can get p naught minus p naught square plus p naught minus p naught square. Alright. So here it's given that what is the p naught value in the question, right? P naught is 0.2 and p1 is 0.8. P naught is 0.2 and p1 is 0.8 is given, right? That is, we have to substitute here the value. It is 0.2 power 2 plus 0.25 into here 0.2 minus 0.2 square is 0.04, right? Plus 0.2 minus 0.04. So it is equal to, what's the value? This is 0.12. The size of the test is, and here the size of the test is 0.12. Understood? Then we have to find the power of the test, right? Power of the test. What is the meaning of power of the test? It's the probability of rejecting H naught under alternative hypothesis, right? That is expectation of phi of x under alternative hypothesis. In here, what is alternative hypothesis here? That is probability of H1 p equal to p1, right? Here alternative hypothesis is, in this case, H1 p equal to p1, right? Then power of the test is expectation of phi of x under p1, right? Here power, not power function, it's a power of the test, right? That is expectation of phi of x under alternative hypothesis. That means here p1, right? So here, which is equal to, like the similar procedure, but we written in size of the test, right? But in the case here, all are here p naught, right? But in power of the test, it all are, instead of p naught we can write p1, right? That means 1 into probability of x1 plus x2 equals 2 plus 0.25. From the test function we can write it as, right, 1 into probability of x1 plus x2 equals 2 plus 0.25 probability of x1 plus x2 equal to 0 plus 0, right? So it's equal to, so simplifying these terms, then we can get this value, right? So we can write here under p1, right? That is p1 square plus 0.25 into p1 1 minus p1 plus 1 minus p1 into p1, right? And then substituting value of that, it is p1 square plus 0.25 p1 minus p1 square plus p1 minus p1 square. Then substitute value of p1. What is p1 value here? 0.8, right? And here 0.8 square plus 0.25, then 0.8 minus 0.8 square plus 0.8 minus 0.8 square, which is equal to, so you have to find what is the value of power of the test. Is your homework. Okay, then we need to find out what is the power function. What is the power function of the test? What is the power function of the test? Power function of the test equal to the probability of rejecting H0 under parametric space, right? That is beta of p. Here parameter is p, right? So we can note it as p. Beta of p equal to expectation of phi of x under parametric space, right? Power function of the test means the probability of rejecting H0 under for the various value of parameters under parametric space, right? That is expectation of phi of x under parametric space p. So here it's equal to, what is expectation of phi of x here? That is 1 into probability of x1 plus x2 equal to 2 plus 0.25 from the test function. x1 plus probability of x1 plus x2 equal to 0 plus 0, right? And the parametric space, which is equal to your next, like simplification, we can write this p square plus 0.25. so you should write all the simplification here, okay, in your notes. Then 0.25 into p 1 minus p plus p 1 minus p, right? It's equal to p square plus 0.25 into p1 minus p 1 minus p plus p1 minus p, right? So we can simplify these terms as, we can write probability of p square into here 0.2, right? Here, but it here 2 times, right? So we can write 0.25 into 2 probability of 1 minus p, right? Here 2 times, right? p1 minus p in plus p1 minus p. So we can write 2 into probability of p1 minus p, right? That is equal to p square plus 0.5 into p1 minus p. This is the power function of the test for all value of p, where p is less than for p is 0 less than p less than 1, right? This is the power function of the test, that is p square plus 0.5 p into 1 minus p. So you have to find out the power function of the test for various values of p here. So you now can write as, you can take some values here, 0.1, 0.2, 0.3, 0.4,